Hello everyone, I welcome you all to this class. This is mathematics class and we are here again to consider another important topic, improper integral. Now we'll be looking at the integration in which the interval of integration has infinity. You know infinity is not a real number. So such a integral is an improper integral. So you see integral of the form having infinity in the interval. So let's look at how we can perform such integration. Now we define the following improper integrals. Integral from a to infinity of f of x dx to be equal to the limit as L goes to infinity of integral of a to L of f of x dx. We are replacing infinity because infinity is not a real number. That's why this integration is improper integral. So we need to evaluate this as L goes to infinity. So we are replacing this infinity with what? A real number L. So we now evaluate the limit of this integration as L becomes large, approaching infinity. So this is the definition, and another definition is integral from negative infinity to a positive infinity of f of x dx. You can break the integration into two to be equal to integral from negative infinity to 0 of f of x dx plus integral from 0 to positive infinity of f of x dx. So this is the way you can break it down. Then for this first one, we have that the definition is limit as L goes to negative infinity. So we now replace this negative infinity with L as L goes to negative infinity, or integral from L to 0 of f of x dx plus limit as L goes to infinity of integral from 0 to L of f of x dx. So this is the definition of this improper integrals, and we say that this improper integral exists if the limit of this if the limit of the integration exists. So if the limit of integration exists, then this improper integral also exists. So when do we say that the limit exists? If the limit is giving you, if the limit of the integration is a real number, then it will exist. But if the limit of integration is infinity, or positive infinity or negative infinity, or undefined expression, then this integration does not exist. So let's look at this example one. They say we should evaluate this integral. Of course, if you look at the interval of integration is having infinity. Solution. So let's look at the solution of this. So we have integral from 0 to positive infinity of we have 3 divided by 1 plus x squared dx. Of course, this 3 can come out of this integration, right? So 3 can come out. We now have 3 integral from 0 to infinity of 1 over 1 plus x squared dx. This 3 here, we factored out. We can write it first, right? So we can write this 3 first. Then this now, we define it. As contour we defined this improper integral. So we define this to be what? Limit as L goes to, we are replacing this infinity with L, as L goes to infinity of integral from 0. Instead of this infinity, we replace it with what? L of 1 over 1 plus x squared dx. So now the question is, what is integral of 1 over 1 plus x squared? Now anytime you have integration of this form, integral of you have, let me say 1 over you have a squared plus x squared dx. Anytime you have integration of this form, if this variable here is having squared, then you can use this method. You have integration, you have 1 over, so you have a fraction 1 over you have a number here. A is a number. Then this is a variable you are integrating with respect to, and this variable is raised to power 2. So now this thing, the answer to this will be what? What is the square root of a square? You take the square root of this. What is the square root of a square? Square root of a square is what? A. So the answer of this is you do 1 over a, you write tan inverse of, what is the square root of this x square? What is the square root of x square? X divided by what? Divided by this square root of a square divided by what? A. Because square root of a square is a. So this will give you the answer of this. So this will be equal to, let's write our 3 limit as L goes to infinity of, now from what I wrote down, so let me write what I wrote down before. Integral 1 over a squared plus x squared dx. Now in this number a squared is what? 1 here, right? Of course, the major thing is that you have plus here, you have a number here, and you have this variable you are integrating with respect to squared. So we have x squared, just like this one. So this number here is this number here. So if you take square root of 1, you are going to get what? 1. So according to what I told you, you are going to put that 1 here. So you do 1 over 1. 1 over 1 is what? So 1 over 1 is still what? 1. Right? So if you do 1 over 1, then tan inverse of, so we have what? X over a. Right? So what is our a? A is what? Square root of this number here. Square root of 1 is 1. So you will now have x over 1 which is what? Which is still x. So tan inverse of x. You can say tan inverse or you say arctan. They are the same thing. Let's write the range of our integration. What is the range of our integration? The range of our integration is what? From 0 to what? L. That's our range of integration. So I've written it down. Then this will be equal to 3 limit as L goes to infinity of, let's evaluate let's substitute the range here. So you know, after performing your integration, if you have a range like this, you substitute it. So let's substitute the upper range. So substitute L for x here. So you have what? Tan inverse of what? L. Then next you will do what? You will do minus, then substitute the lower range. That's 0. Tan inverse of 0. So we are taking limit as L goes to infinity. So we'll put infinity for L here. You now have what? Tan inverse of infinity. Minus, what is tan inverse of 0? Tan inverse of 0 is what? 0. So you have 3 into, what is tan inverse of infinity? Tan inverse of infinity is 90, which I can write as pi over 2. You know, 90 is the same thing as pi over 2 in radian. So pi over 2 is simply 180 divided by 2, which is 90. So this is what we have. Of course, minus 0. So we'll have this back. So if you multiply by 3, you now have 3 pi. So we are going to have 3 pi divided by 2. So this will be the result of this integration. So thank you so much for being part of this class. I'm expecting you in our upcoming class as we solve more questions under this topic. Bye.